So we are now already live, waiting for people to get in. Welcome, Trevor. I'm trying to age today. Oh, I see a puppy. Hello, Charlie. Is Cooper there?
Yeah, I'm here.
All right. Here you
His
are
name's
first
Romeo.
time, but I have like 6 people in. Everybody is kind of still somewhere else. Are you saying something, Trevor?
Yeah, I was just saying his name's Romeo.
How is?
Romeo.
Can't hear you.
I was just saying his name is Romeo.
Oh, Romeo the doggy. Okay. I always admire pets from far. I never got some. We have William, James, welcome. So we'll be talking today about reduction of order or second order differential equations. When you have an equation, you have one solution and you can use reduction of order to find a second solution and write the general solution of the equation. As of now, we got only half of the class in. So be careful, guys, it's already online, so nothing funny. All right, so it's already 2 minutes into class time, and what we are going to do is move on. If, for instance, we have an equation of the form a of x second derivative plus b of x first derivative plus c of x times the function equals 0, and y1 of x is a solution. So you know one solution of the equation called y1 of x, and the equation is of the given form. And two questions here. Usually we ask, find a second solution, or we ask to find the general solution. So these are the two things that you can be asked to do when given an equation of this form that you already know one solution of. Okay. And the method here is reduction of order. Order of what? Reduction of order of the equation. So we have this equation, which is a second order equation, and we are going to apply reduction of order to switch this equation to a first order linear differential equation that we will solve. Instead of solving a second order equation, we solve a first order equation. Okay. Now recall, last time we used the fact that for a differential equation of the form y double prime plus p of x, y prime plus q of x, y equals 0, the Vronsky of any two solutions satisfies w of x equals c times e to the negative integral of p of x dx. We used this last time. So for any equation of this form, the Vronsky of any two solutions is a constant c times e to the negative integral of p of x dx, where p of x is the function that you have right here in front of the first derivative. And the coefficient of the second derivative is 1. And this is what we are going to use today, along with another property of the Vronsky. So that's one thing. Now the second thing is, so if y2, or say just y, is another solution of this equation, then w is actually defined as y1 prime, y2 prime. And this is y1 y2 prime minus y1 y2 minus y1 prime y2. Okay. Now, if we take y, okay, I wrote y2, then let's keep it y2. Like if we take y2 as a function of x times y1, so we want to look for that second solution y2 as a function u of x times y1. So we defined u of x as the ratio y2 over y1. That's technically what it is. Then you would see that here u of x, which is y2 over y1, leads to u prime of x equals derivative of this ratio, that's a quotient rule, that's y2 prime y1 minus y1 prime y2 over y1 squared. And guess what? Check, what is this on top here? That is exactly this thing, which is w. So that is w over y1 squared. So if I'm looking for y2, which is another solution of this equation, in the form u of x times y1, where y1 is the known solution, then the derivative of u is w over y1 squared. That's pretty good. And so this gives me a hint on how to solve this problem. So steps. In step 0, if we call this equation star, if we call that original equation star, we say standardize the equation, standardize the equations. Which means bring it to the form y double prime plus p of x y prime plus q of x y equals 0 by dividing the equation by the coefficient of the second derivative. You get that. First step. Now, on step 1, we do what we just did here. Say, let y2 equals u of x y1, where y1 is the given solution. All right. And you find w c e to negative integral of p of x dx. Find that. All you need to do that is read p of x from the equation, put inside that integral, you get it.
I have a question. What is that last one, which says y second prime plus p of x y prime plus, is that p of x again?
U of x. So after finding w, the second thing you do is you find u prime of x is, as we just found here, w over y1 squared. So the w that you just found over the square of the given solution. And the next step, integrate to find u of x. So you integrate both sides of that equation, you get u of x. And once you get your u of x, here you will have two constants. You have two constants when you integrate. Why? Because you have one constant here in w, And when you integrate w here, another constant of integration shows up. So you have two constants of integration in there. And then after finding u of x, write y of x equals u of x, y1. This gives you the general solution of the equation, provided that you have those two constants in it there. And now if the question is asking you to give a solution, then you can pick one of the solutions that you have by just giving some values to the constants that you have to get a second solution. Because right here in this method, you already give the general solution of the problem, and it's really like 4 steps, right? Any questions? So that's it. Let's see what an example would tell us. So in the first example here, we got x example 1, your x squared y double prime plus x y prime plus y equals 0, y1 of x equals cosine of natural log of x. That's the problem. Again, and this is one of the times when I stop to say, again, be very careful when you read the question. Make sure you understand what the question is telling you. You will see this kind of problem somewhere else in this course where another method will be given to you to solve it. But right here, it says reduction of order. And what you need to do is apply that reduction of order, not show me what else you know. So we are going to do reduction of order on this thing. And when we say step 0, standardize the equation. So we divide by the coefficient of the second derivative. That's the standard form. And so right here, we see p of x. Then we go to step 1. We say y of x equals u y1. And that's what we want. And w, which is the Vronsky of these two, is c e to the negative integral of p of x dx. And so we find that w is c e to negative integral of dx over x, because that's what p of x is, 1 over x. So that's c e to negative natural log of x, because the integral of dx over x is natural log of x. And so that's c e to the natural log of x to the power minus 1. So that is cx to the power minus 1, which is c over x. So that's w. Then you go to step 2, and you get w prime, u prime. You get u prime of x equals w over y1 squared. W is c over x divided by y1. Y1 is cosine, so that's cosine squared of natural log of x. So this is c over x cosine squared of natural log of x. That's it. No other work to do, just write that. And then on the third step, you gotta integrate what you got there. So you get u of x, integrate. So you get u of x equals c integral of dx over x cosine square of natural log of x. So that's what you get when you want to integrate. And now, how do we integrate this? That's your skills that show up now. Any advice?
Could we use u substitution and set u equal to natural log of x?
What's that, sir?
Could we use u substitution and set u equal to natural log of x?
Yeah, just that now, because we have u here, we need to call it something else, right?
Oh yeah,
So we
like
could
w,
say,
I guess.
yep, good.
Yeah.
So equals natural log of x. And so dv is dx over x. That's what we do, substitution. And so this gives us c integral of dv over cosine square of v. And what's the integral of dv over cosine square v? Anyone else? This is a standard table integral. Michael?
Yeah.
Yep, question, what's this integral equal to?
See, cosine. That's great. I always forget. I always mess up with this, the cosines. Would think ln, but no.
Don't have it.
Yeah, sorry, I'm blanking.
All right,
Isn't
I'll
it
go ahead.
tangent?
Messi, what?
Isn't it? Because you could think of it as, instead of 1 over cosine squared, you can think of it as secant squared, and the integral of secant squared is tangent.
Oh, yeah.
Tangent, right? It's a table integral, like I said, so you need to look up that in that table and see and find that. So here it's tangent, and like I said, when you integrate, you don't miss out the constant of integration. So and you can see that when after integration, you have now 2 constants in this function, u of x. And then in the next step, okay, you just write y of x equals, as said at the beginning, u y1 of x. And u is c tangent of x plus c1 times cosine of natural log of x. And this is c sine of natural log of x plus c1 cosine of natural log of x. And that's the general solution of the problem.
Wouldn't it be? Would it not be c tangent of the natural log of x? Because like you would have to replace b, or is it?
Yeah, that's tangent of natural log.
Okay,
That was tangent of b, okay. And then here that's natural log of x, sorry. And I actually simplified here, look, taking into account that it's tangent of natural log of x.
So how does it go from tan ln of x to that sine ln of
10
x?
times cosine is sine.
What would you say?
Tangent times cosine is sine.
Okay.
Because you're multiplying here, tangent times cosine, that's sine, plus c1 times cosine.
So tan, you can rewrite tan as sine ln of x, cosine ln of x.
Yeah. That's the definition of tangent x is equal to sine x over cosine x. Are there questions on this? Does it make sense, the method? You see, it's pretty straightforward, right? If you follow the steps, there's no reason why it wouldn't work. 4 steps. No more questions, I guess, by the silence. All right. Now let me give you this example for you guys to follow. Example 2. So the equation is y double prime plus 2y prime plus y equals 0. And then y1 of x equals x e to negative x. So this is the solution that is given. And you need to follow the steps to find the general solution. Oh yeah, with this silence, usually it's actually better that I let the music on. So calm, like it feels there's nobody here. Anybody with something to say? Okay, we are missing about 8 students today, almost half of the class.
Is there any part in the steps where, well, for P, did you get the W to equal C times E to the negative 2x?
We need to go step by step on the answer. I don't write the answers ahead of time. We worked out through the problems. So all the problems I'm actually solving with you guys, I don't have the solutions written anywhere. We just go as we go. Okay. So if you want, let's start by the first step. What's your step 0 here is not necessary because we have the standard forms. So what you got on the first step?
I wrote out that y2 equals u of x times y1. And then after that, I got w
Mm-hmm.
equals to c times e to the minus the integral of 2. Is that right?
Yep, that's correct. So that is C, E2.
E to the negative 2x.
That's it. It's correct.
And then after that, we take a u, the
E prime.
u prime equals the ce, well, w over y1 squared.
Yeah, always put that down to make sure that you remind yourself what you're using. So that is correct. Y1 squared is x e to negative x squared. And now you do the algebra. That's C e to negative 2x. Often here people mess up because of the algebra that they do. X e to negative x squared is first x squared times e. Negative x squared is negative 2x, not x squared. And then the e to negative 2x cancel, and you have c over x squared. So that's u prime. And then our next step is integrate. You get u of x equals c integral of dx over x squared. And what's the integral of dx over x squared?
1 over x squared. 1 over x.
Something is missing.
Is it 1 over x or negative 1 over x?
Negative 1 over x. So that's negative e over x plus a new constant. And now you can actually suck into the constant that negative, so that becomes c2 over x is c1, where c2 is the opposite of c. And then you can multiply here to get y of x equals that u of x times y1. And this is c2 over x plus c1 times x e to the minus x. And then you cross multiply this, you get c2 e to negative x plus c1 x e to negative x. That's it. So that's the general solution. And again, we will have other topics in this class where you will see this equation and we will solve differently. But again, here, the problem is about the method, learning how to apply the method. Any questions? So here, if the problem was find a second solution, we would say you could pick y2 equals e to minus x. Just take any values of C1 and C2 and put in there, and whatever you find is a second solution. This is C2 is 1, C1 is 0. You pick any two different values of C1 and C2, you plug in there, you got a new solution. Are we good? And here we would say also that e to negative x and x e to negative x form a fundamental, I'm going back to the topic of previous lecture, a fundamental set of solutions. Why is that? Because we actually claim that this is the general solution. If this is the general solution, then by what we had last time, these two functions form a fundamental set of solutions because the equation is second order, and these are the basic functions that we found in there. You can also show that the Avronskin is not 0 because that's the Avronskin. The Avronskin is a constant time e to negative 2x. It's not 0. And each of them is a solution because we have shown that these are all solutions of the equation. All right? Is there any other question on this topic? For me, I think it's a pretty straightforward topic. If you don't have any further questions on it, then I'm going to move to start section 4.3. This is section 4.2, okay? And it's all that we're gonna do there. Is there any question? All right, if there's no question, then we will start 4.3, which is one of the longest sections that we will have. Homogeneous linear equations with fixed coefficients. So those are equations of the kind an, y, n, nth derivative, n minus 1, n minus first derivative, all the way down to a2y second derivative, a1y prime plus a0y equals 0. Homogeneous in this problem means that the right-hand side is 0. It's linear because you don't have any products of the functions y prime all the way to y to the power the nth derivative. Fixed coefficients because these numbers are not functions. A0, A1, A2, all these are not functions. It's just numbers, okay? Examples, second derivative minus 3 times the first derivative plus the function equals 0. For third derivative minus second derivative equals 0. 2, fourth derivative minus the function equals 0, and so on. These are all examples of linear equations. This is a second order because second derivative is there. Third order because the third derivative is the highest derivative. Fourth order because the fourth derivative is the highest. So those are all linear, homogeneous differential equations with fixed coefficients. The coefficient here is 1, -3, 1, 1, -1, 2, -1. So you don't have a function in the coefficients, no x showing up in the equations. That's what it means, fixed coefficients. And our job in this class, starting from now, is how to solve these equations. That's a basic question. And the theory on these questions relies on one key fact, that when you take, if you have a function that is e to the power, say, lambda x, then the derivative is lambda e to the lambda x. The second derivative is lambda squared e to the lambda x. So no matter how many times you're taking derivatives of this function, you're always going to have e to the lambda x showing up being the only function that involves x, and everything else will just be the coefficients coming down. And if that happens, and you take those derivatives and plug into this equation, what is going to happen is that everything is going to simplify and you will have an algebraic equation. So if we plug this in the equation, if we plug these into the equation, we get an lambda to the power n plus an minus 1 lambda to the n minus 1 plus a2 lambda squared a1 lambda plus a0 equals 0. Because when you plug that in, you have a common factor that is e to the lambda x, which is never 0. You can divide by that, and you can get this. This thing is called the Euler equation. Now, after noticing this, that if you take such functions, you take derivatives and plug in, you get this, you realize that any equation of this form can actually give you n values, n different values of lambda. If we're thinking in terms of complex numbers, that's always the case. And so if that is the case, then each of them is going to give you a solution, and therefore you're hoping you will have as many solutions as the order of the equation, and therefore you'll be able to form a fundamental set of solutions. That's why. Say, moreover, when lambda 1 is not equal to lambda 2, the functions e to lambda 1x, e to lambda 2x are linearly independent. We showed that in the previous lecture easily. And because of that, if we have a second order equation, then we have hope that if we get two different lambdas, then we have linearly independent functions, 2, for a second order equation that solve the equation, then they will form the fundamental set of solutions as said last time, and therefore the general solution can be written using these functions. That's the idea, all right? Now, when you'll be answering questions on a test, you don't need to go ahead and do all of this. That's just to explain why we use the method. Now, how do you solve the problem? That's the thing. The first thing, of course, is second order. For the easiest equations, second order equations. That's the form a y double prime. So a2 plus a1 y prime plus a0y equals 0. That's what you call second order linear differential equation with fixed coefficients when a2 is not 0. So when you want to solve such an equation, the first thing you do is you get the Euler equation, which is what you have here. Just replace the derivatives by powers of lambda. So that's a2 lambda squared plus a1 lambda plus a0 equals 0. You write down the Euler equation, then you solve it. And then third step, write the answer. Very easy. Get the Euler equation, solve it, write down the answer. Following the appropriate case. This is where it is funny. Following the appropriate case. And what is that? The thing is that when you solve this equation in general, it's a second order equation. We have a formula to solve that, which we call the quadratic formula. You have three cases. First case, case 1, you get two solutions. Lambda 1 not equal to lambda 2. Real numbers. Therefore, your solution is y of x equals c1 e to the lambda 1 x plus c2 e to the lambda 2 x. That's what you would do. Case 2, two equal solutions. lambda 1 equal to lambda 2. Here we say of a repeated root. You have a repeated root, then your solution is y of x equals c1 e to the lambda 1x plus c2, and you multiply by x first, e to the lambda 1x. And then you have a third case, 2 complex conjugate solutions that can be written as alpha plus minus I times beta. If the two solutions of the equation are written as alpha plus minus I times beta, where this I is the imaginary unit, then your answer will be y of x equals c1 e to the alpha x cosine of beta x plus c2 e to the alpha x sine of beta x. That's the rule. The most challenging thing is to be able to appropriately choose the case, right? If you know your algebra on how to solve this equation, then everything is easy. You get that answer, you identify the case, and you write down the solution. Full stop. Now, if you have initial values, then you have a fourth step. As in all the problems that we have been solving till now, initial values always indicate a last step. Use initial values, it's given. Okay. Is there any question on the procedure itself before we get to the questions? Examples, I mean. Is there anything you guys want to explain here before we look at the examples? All right. So we go example 1. 4 y double prime plus y prime equals 0. So right there, step 1, write the Euler equation. 4 lambda squared, replace derivatives by the lambda powers of lambda plus lambda power 1 equals 0. That's it. You can either use the quadratic formula or just solve it in any way you want. That's algebra. It's up to you. So right here, I figure I can just factor this thing out and solve it. So that's lambda times 4 lambda plus 1 equals 0. So lambda 1 is 0. Lambda 2 is negative 1/4. It doesn't matter which of them you call lambda 1 and which you call lambda 2. So that's it. Wrote the equation, solved it, got the answers. The two answers are different and real. So that is case 1. Different roots, real numbers. So that's how you write the answer. So that's y of x. It's really short answers in these problems. C1 e to the 0x plus C2 e to negative 1/4 x, and that is C1 plus C2 e to negative 1/4 x. That's it. No story, no long explanations. Nobody needs them. Example 2. You can have 4y double prime plus 4y prime plus y equals 0. Again, step 1. Write that Euler equation, 4 lambda squared plus 4 lambda plus 1 equals 0. Solve this equation. Here, for me, I will see 2 lambda plus 1 squared equals 0. This is what that equation is. And because it's squared, that tells me I have a double root because of the square on this thing. So lambda 1 equals lambda 2 equals negative 1/2. And this square here calls for what we call the multiplicity of the root. That's why it says twice, because that's squared. That will be important in the other section when we get there. So it's good to start getting acquainted with it. Now we got two answers. The two answers are equal, and you look at the procedure. The procedure says when the two solutions are equal, that's case 2, this is how you write the answer. C1 e to the lambda plus C2 x e to the lambda. So my answer is going to be y of x equals C1 e to negative 1/2 x plus C2 x, then e to negative 1/2 x. Why? Because that is a double root, right? Or repeated. Example 3. Okay, have y double prime plus 16y equals 0. Y of 0 equals 2. Y prime of 0 equals negative 2. All right, I let you guys do this one. And tell me what you think the final answer is gonna be.
wouldn't this get to the part where we had the imaginary because we would get lambda to equal to like the square root of a negative 16, but you can't take that square root, so you have to use the imaginary number.
Yeah. Square root of negative number gives rise to the I. No, first of all, give me what's your Euler equation you got here.
Lambda squared plus 16
Yeah,
equals 0.
that's it.
And then you have the lambda squared, or
Continue, I'm listening.
the lambda squared equals negative 16, and then you would take the square root of that. And then that's, I guess that gives the 4, is that 4i? I don't know. I don't know how that comes out. Like, I don't know what's after that step right there.
And always remember when you have a square and you want to find the answer, it's always plus minus because you got two answers. And now here, square root of 16,
It's just
16 is square root is 4. And square root of negative 1 is I. So that's plus minus 4.
4i. Okay. That's the part I don't know what to do after that step, because I got plus or minus 4i.
Mm-hmm.
But I don't know what to do after that step.
I understand that. Now, when you go here and in the steps, that says when the two complex roots are alpha plus minus I beta, and in this case, we found the two roots to be plus minus 4i. What does that mean alpha is?
Is it just lambda?
No, that's lambda and that's lambda. So what is alpha for this lambda and what is beta?
Alpha would be 0 and beta would be 4.
That's it. Alpha plus minus I beta, that's what it is. So alpha is the part that comes before plus minus, is nothing there, so it's 0. And plus minus 4, so beta is 4. So right here in this answer, alpha is 0, beta is 4. And that's what goes into this answer. C1 e to the alpha x cosine beta plus C2 e to the alpha x sine of beta x. So you identify alpha and beta from the answer you get here. Are we good? All right. So therefore, in this answer, we will have y of x equals C1 e to the alpha x. Let me write completely the answer before putting the numbers. Plus C2 e to the alpha x sine of beta x. C1 e to the 0 cosine beta x. And beta is 4. C2 e to the 0 sine 4x. And that gives you C1 cosine of 4x plus C2 sine of 4x. That's the final answer for that part. But unfortunately, in this problem, it also said y of 0 is 2 and the y prime of 0 is negative 2. So we got to use those. And therefore, we need to find the derivative also here to make sure we can plug in 0 and -2 into that as well. Derivative of this is -4 C1 sine of 4x plus plus 4 C2 cosine of 4x. That's the derivative. And so y of 0 equals 2 implies what? I plug in 0 for x. Cosine sine of 4 times 0 is 0. Cosine of 4 times 0 is 1. So that's C1 plus 0 equals 2. Right away, you get C1 equals 2. Y prime of 0 equal -2. That leads to this one. When you plug in 0, sine is 0 plus 4 C2. Cosine of 0 is 1 equal -2. So you get C1 equals 2. C2 equal -1/2. So you got the two values, and then the only solution that satisfies those conditions is C1 2 cosine of 4x minus 1/2 sine of 4x. And remember that the initial value problems always has a unique solution in this setup. So once you have y and y prime given for a second order equation, there's only one answer that you will find. You will be able to find C1 and C2. Questions? Is it clear now how we do? Now let me on one last example here. Write in general the formula how you could use a quadratic formula to solve those questions. Example 4. Next time we will continue on this topic with higher order equations, which means equations of order greater than 2. So let's say y double prime plus 6y prime plus 5y equals 0. Y of 0 is 0. Y prime of 0 is 3. So first thing, Euler equation. It's going to be lambda squared plus 6 lambda plus 5 equals 0. And now what you do is you can use the quadratic formula lambda 1, 2 equals minus b plus minus square root of b squared minus 4ac over 2a. This is what you call the quadratic formula, right? And that's for an equation of the kind ax squared plus bx plus c equals 0. So a is the first coefficient, b is the second, c is the third. So that's what you call the quadratic formula. Whenever the equation is second order, if you're really not good at algebra, don't try to factor out or do what I did there. Just write down that formula and plug in the numbers to see what you get. Otherwise, you get the wrong roots. You mess up your entire problem, and then you cry for partial credit that you don't see. Because sometimes when you mess that up, it completely changes the problem, and it's really hard to give you partial credit at some point. So here in this problem, A is 1, B is 6, and C is 5. So that's A1, B6, C5. And you do negative B. B is 6, so that's minus 6 plus minus square root. B squared, that is 36, 6 minus 4 times A1 times C, and C is 5. And always suggest to put parentheses around these numbers when you're doing that, because some of them might come with negative signs and then you forget the sign. Over 2A, and A is 1. So that is -6 plus minus square root of 36, and then minus 20, that's 16 over 2. Now, the hint is when you get on a square root here, if you get a negative number inside there, you do what we did on example 2. You get the I for square root of -1, and then you get the square root of the number that comes. Does that make sense? So that's a general rule. You just apply this, and at the end here, you check. You got a negative number, I comes. Don't have a negative number, there's no I. Square root of 16 here is just 4. If that was square root of -16, as in the previous example, you get 4i. And so here, we're gonna write down the answer. So square root is 4, -6 minus 4, -10 over 2 is -5. -6 plus 4, -2 over 2 is 1. So the two answers are -5 and 1. And those are two distant roots. They are distant, so that's case 1. So y of x equals c1 e to -5x plus c2 e to the x. And now you use initial values.
Wouldn't it be -1?
Oh yeah, sure. Thank you. Because you got -2 over 2, that's -1. Okay. And so here, you plug in 0, you get y of 0 is 0, so that would tell us plug in 0. Y of 0 equals 0. That gives us c1 plus c2 equals 0. Then you got y prime of 0 equals 3. And y prime of 0 is, you take the derivative of this to get y prime. So you get y prime is -5 c1 e to -5x minus c2 e to -x. That's the derivative. And now you plug in 0, so you get -5 c1 minus c2 equals 3. First equation, c1 plus c2 equals 0. You can solve, you get c1 is -c2. You plug that in here, so you get 5 c2 minus c2 equals 3. So c2 equals 3/4. c1 equals -3/4. That's how you get them. And now you got c1 and c2, so you plug them in. Y of x is -3/4 e to -5x plus 3/4 e to -x. And you make sure you write the constants that you found in the appropriate spots. Otherwise, you mess up your problem. That's it for me today. If you have any questions, you can ask. If not, I'll be free to see you next time.
Thank you.
I'll see you guys. Thanks.